Should be here. Join session. Hello. Testing. Hello. Testing. Okay. Okay, this works well. Right. Right. Welcome to Thursday's lecture. So a couple of announcements to make before we get started. So assignment 1 will be released tomorrow, definitely. And another thing is that I think we made an announcement that if you missed quiz 1, there is a makeup opportunity for you. So we made a basically, we made a quiz just in case you didn't know, you didn't get that. Click Activities, and you can do the quiz 1 sub. And this is the only time we'll offer you a sub quiz because apparently in the first few weeks, it tends to be pretty chaotic, and people don't know where to find the course material. It's pretty understandable. So we're giving you one-time extension for a replacement for the quiz 1, and please remember to do quiz 2 and the other quizzes. So every quiz is due on Friday at midnight, and so tomorrow at midnight, quiz 2 is going to be due, and quiz 1 sub is going to do as well. And for people who have already taken quiz 1, if you want to take quiz 1 sub, you can do that as well. We'll take them. We'll select max from your 2 attempts. So because quiz is kind of a way for us to push you to, kind of like a reminder to, you got to study for this course. So we don't want people to, kind of miss out and lose marks just because they didn't know where to find it. All right. And so today we're going to talk more about querying in SQL, and we're going to talk more about some SQL syntax and we're going to talk about the with clause, and after that we'll talk more about procedural programming in SQL. So basically SQL is kind of like a declarative language where if you think about it, SQL was created like 20-30 years ago, and it was so powerful and it was so easy to use that it kind of mimics natural language. But 30 years, actually 40 years after they developed this thing, now we have something called a large language model, and people are actually using natural language to write programs. So if you think about it, it's pretty nice. And but beyond SQL, we still, if you want to solve more complex questions, and if you want more functionalities, and if you want to implement a trigger, things like that, you need a procedural programming component as well, just like you do in C++ and Python. So that is what a PLPG SQL language is for. So we're going to talk more about that in the second half of the lecture. So today, let's look at another version of the BEES database. So in the database, we have the drinkers table, the beers table, bars table, and sales table. So you can look at these tables here. And for ease of presentation, I have included, so you don't have to worry about not being able to access this website. So this is actually, this is the online version of this course, and I find it easier to use their PostgreSQL playground. So basically, it's easier for us to demonstrate stuff and things like that. So you don't have to worry about, I can't access DZ and 93.1. So that's okay. You're not supposed to. So this is the schema of the database. We got a bunch of. Do we have a ER diagram here? Okay. So we got beers, we got people visiting bars, and each one has a nice primary key. So beers have the beer name, which is the unique identifier, and we got the drinkers' names, and bars have names, and then we're recording the interaction between people and the bars, and people and beers, as well as bars and beers. And all of them are many-to-many relationships, partial participation. So we need 1, 2, 3 tables for the entities, and then we need 3 tables for the many-to-many relationships. And they're all partial participation. So the mapping is pretty straightforward. So we need 3 tables for those, and then we need 3 tables for these relationships. And let's look at a couple of questions, and so that we can learn more about subqueries and via these examples. So a typical kind of query is we want to fetch the data that corresponds to the maximum. So we not only want the maximum, we also want the rows that corresponds to the maximum. And the one way to do that is to use subqueries. So here we could write something like this, and imagine we have an X table. If we do the query within here, it is selecting the maximum size on an item or on an entity, and then we match that maximum size with the size in the original table, and then we select the name of the entities with that map to the maximum size. So here, in this way, we're getting the objects with the maximum size. So let's look at a more concrete example. So here, so this is where we can also use subqueries. So we want to solve a classic question: what bars sell beers that John likes? So if you look at the schema, before we do anything, we need to look at what tables does this query concern. So let's look at the tables. We got beers, bars, drinkers, sales, and likes. So obviously we need the table likes, we need a table sales, and do we really need the drinkers table? Because we need to map the name John, so I think we need to, it depends on whether sales stores the drinker's name in that table. So let me see that. So for sales, it does store the drinker's name and bar's name. So one way of doing this is that we can first find the beers that are liked by John. So that corresponds to a subquery here. And then we can find all of the bars that sell any of those beers from the sales table. And we can put them together in this way. So basically, we're looking for bars in the sales table where the beers are matching the beers liked by John. So let's do a demonstration of that. So here, this is already like a PostgreSQL shell, which is pretty nice. And I'm not sure if we have any tables in here, so nothing, great. So let's load the schema first. Schema. Tab, okay. So everything's loaded, and we can go, I think it's stored in here. So if we do that, we'll find all of the beers liked by John. And we want to match these beer names in the sales table. So the sales table looks like this. So the sales table looks like this. We want to fetch this, we want to go through every line in every row in this table, and then only match the rows where beer is one of these. And after we match that, we want to return the bar name. So that's essentially what we're doing here. So this is a subquery. So this is a subquery. This is the main query. And basically, this is how you get this question. And another thing that we need to talk about for this question is that there is an alternative way to do it. As you can imagine, we can also use joins. A lot of times, whenever you encounter a question where you can use subqueries, you kind of have to ask yourself, can I solve this question with a join? Because if you phrase it like a join, it is usually more efficient, and it is usually it will get a better execution plan from this PostgreSQL engine. So instead of doing this, instead of using a subquery, we can basically match the table. We can basically join the tables that we are interested. So basically, for sales and likes, we can join them on the beers column, and then we can basically match the drinker to be John, and it will give us the same result. And this is a small database, so probably the efficiency difference is not very large. But when you have like a huge database in industry, they tend to differ quite much. And so this is another question where we might want to use subqueries. So this is actually a more complicated question than the other one, because in this case, we're asking what is the cheapest beer at each bar. So essentially, we cannot really solve this question in 2 steps. So in this question, we can first find the beers, and then we can map the beers to the sales. But in here, we're essentially asking a question for every bar. Oh my God, I shouldn't touch that. Okay. We're essentially asking a question for every bar. So every bar, we need to find the cheapest price in this bar, and then we need to match the name of the beers with this price. So this becomes a correlated subquery. So basically, we need to go through every row in the sales table, and then we need to kind of look at we need to look at the minimum price of sold at each bar, and then we need to match that price to the sales table to get the beers at each bar. So this becomes like so this is the inner query, and this is the outer query. And the reason why this is a lot of times problematic is because the inner query is correlated with the outer query. So here we're saying that the outer query is looking at the sales table, S, and then the inner query is looking at the sales table as well, but it needs to match the bar names. So basically, what it does is that it goes through every row in sales, and then for that row, it needs to go to every row in sales again to see the minimum price sold in this bar. And then you need to map it back to get the bar and beer and price names. Bar and beer names and prices. So let's look at how it... And notice that when we're demonstrating this, the inner query is actually executable because it is not dependent on the outer query. And in this case, it is a lot easier to kind of transition that into a join. But in here, we kind of have to write it as a correlated query because this part of the query, we cannot really execute it because it depends on the outer query. So we can see what that does. So this gives us the beers that are sold in the are the cheapest beers in each bar. Okay, and here this is this is probably the most difficult part to understand. So I will try to do it slowly. So a lot of times we need to answer queries like which X are related to all Y's. So it sounds very strange, isn't it? So let me put it in real sentences. So basically, let's say that we have students take courses. What if we want to find the students who have taken all of the courses? So that is an example of this query. And another example is we want to find the beers that are sold at all bars. So essentially, we want to find the students who have taken all of the classes, or we want to find the beers that are sold in all bars. So this is essentially kind of like a hard problem in SQL, because if you think about if you think about designing an algorithm to do it, this is what would you do. So this is the pseudocode of what you would do if you are not taking database, but you're taking, 1511. What would you do is that for each x, if you want to find the x is related to all y's, for each x, you need to go through every x, and then you need to check whether it is related to all y's, and then if it does, we need to add that to the result set. And the tricky part about this pseudocode is that we essentially need to compare sets directly, and it is very hard to do that in SQL. So to get around it, what we're doing is that usually we're using a double negation to get this result. So first, we look at all of the y's, and then we look at all of the y tuples related to x. So these are two sets. So this is the big circle, and then all of the y's that are related to x is a smaller circle. And let's imagine this. If in this case, for this specific x, it is related to all of the y, then in this case, those two circles will overlap. There will be one circle. And in that case, their difference should be the empty set. So this is what we're looking for. We're looking for the cases where the difference between the bigger circle and the smaller circle is the empty set. So basically, we're looking at all y tuples, and we're looking at all y tuples related to x. The difference is the y tuples that are not related to x. We're trying to match the x tuples that are checking whether the inner query is empty. So basically, we're saying that we want to compute all of the y tuples that are not related to any x, and we want that to be empty. So let's look at the beers example. So if we want to solve which beers are sold at all bars, then I think I have a small. So let's imagine this. So if S1, so S1 is all bars. Let's look at S1 is all bars. And then S2, set 2, so S1 is here. So this is S1, okay. And this will be S2. So S1 is all bars, and what is S2? S2 is computing all of the bars that are selling this beer. So the bars that sell beer B name. So basically, for each beer, we're trying to find the bars that are not selling this beer. Yeah? Yes?
What's not existing except?
Pardon?
What's not existing?
Oh, so that's a good question. So except is, I think we talked about last lecture. So basically, this is a set operator. So if you take, this is one set, this is another set, you can do union, which is taking the union of two sets. You can do intersection, and you can do difference. So difference is basically you're getting all of the items that are in the first set, but they're not in the second set. So that's except. So set difference. And set difference, set intersection, and set union, you should know about that in discrete math. And where not exists is basically checking whether this set is empty. Where exist is checking whether there's at least one row returned by this subquery. If we're saying where exist, then we're checking whether this subquery is returning at least one tuple. If we're writing where not exist, we're checking whether this is empty. So S1 is all bars, S2 is the bars selling this beer. So what is the difference between them? Well, logically, S1 minus S2 will be the bars that are not selling this beer. And let's go back to our original question. What we want? What we want is the beers sold at all bars. So if you're a beer, if you're a beer and you're sold in all bars, then what should you get for S1 minus S2? So if you're a beer, you're sold at all bars, that means that there isn't any bar that is not selling you, that is not selling this beer. So it sounds kind of crazy, but basically if you're a beer sold at every bar, then the bars not selling this beer is empty, it's nothing. So we need to check whether this is empty. So this is exactly what it is doing. We're computing S1 here, we're computing S2 here, we're computing S2 here, we're computing the difference of them, and then we're checking whether it is empty. When that's empty, it means you are the most popular beer in all bars. You're sold in all bars. And let's quickly do the query and see what it does. Okay, there is a beer called New that is sold in all bars. So let me look at the sales. Let me demonstrate. Let me verify whether that's true. So how do I know if that's so? What I like to do is that I like to count the many of times they're sold in each bars. So here it's giving me the cross-reference between beers and bars. So what I want to do is that, what if I want to compute the number of beers sold in each bar? What should I do? What should I use? We should use, when we want to divide them into groups, we want to use group by. So we want to use group by, we want to group by bar, of course. Group by bar. And one thing about group by is that once you say you want to group by something, okay, I think here this is bad. You see that? Once you say you want to group by something, and if you still select everything, it will complain. Because essentially, you're grouping by, you're dividing them into different groups, and now, after select, only two types of columns are allowed. First is the column there that you're grouping them by, which is bar, and the second is some aggregates. So we need to put bar here, and then we need to count the number of beers, I think. Beer, not beers. Okay, so wait, is that right? No, I think we need to. Anybody see what I did wrong? What is the information we need? We actually need how many times they are sold in each bar. So we actually want to group by. Beer. So for each beer, we need to count the number of bars they're sold in. So we should group by beer instead. And you can see that we got the beers and we got the number of times they're sold. And last time I checked, we actually got 6 bars. So the beer called New, with the most number of bars, it should be the result of this query. So the New beer is sold 6 times, and we have 6 distinct bars, which means that beer is the New beer is the beer that is sold in all bars. So what does that tell us? It means that there is another way to do this problem. So this is the original sub-query based way. And we can also use grouping by as well as aggregates to filter out the beers with the soda in all bars. So basically what we can do is that we can group by beer, and then we can map the maximum number of beers back to the sales table, so that we only keep the new beer with 6. So this is what's happening. So this is the end result. So this is the one giant query, and of course you can break that down into smaller views to make it more for better explainability. Okay, so just in case if we were ever going to ask you this question in an exam or something like that, you should be able to have at least one type of solution. You know, you should know at least one of the ways to do this. So if you don't remember this way, you can use the other way, which is based on grouping and counting. And another thing we need to talk about is, so we were just looking at aggregations. So here we are looking at aggregations. This is aggregations. Basically, we're grouping these things by beers, and then in each group, we're applying the count aggregation to it, and then we're getting these kind of like a, what do you call it? A bin plot or a bar plot, a distribution plot. And but sometimes we not only want the aggregate statistics, but we also want to keep the original rows. So let's see. So this is a classic example with students, courses, and marks. And of course, we can group by course. We can group by course and compute the average mark in that course. For instance, in COMP3311, the average mark may be like 60 or 70, and maybe in a postgraduate course, the marks maybe they're usually higher. Maybe the average marks is like 70 something. So, but what if I want information about every student, and then the marks, and then we also want information about the student, the marks, but also we want to compare that with the class average. Well, we actually do that. We do that every term. We have to do that. So if you look at it, so this is the example that we know how to do. So if you look at it, you see that we got course marks from enrollments. We're grouping them by course. We're grouping them by course, and then we're applying the average mark to each group. So to experience with more aggregation functions, we can partly do main. Well, so COMP2521 has a main mark of 45. COMP3311 is mean mark is 60. It means that everybody passed the course. Let me look at the maximum. Max is about the same. So anyways, we already know how to do this, but what if we want to put that information after every student? This is where we need to use partition over. So here, we're also grouping by course, but we're telling them that in the end result, we want to compute a statistic that is based on the partition, but we still want to keep other columns in the end result. And in this case, we use partition. So this is the part that you need to pay attention to. We need to compute average mark for each course, and then we need to attach that where possible back to the original table. So let's look at. So this is wrapped in a view, which is nice. And let's look at the view. So the good thing about the view is that you can treat it like a table, but it's not a table until you use a materialized view. But we'll talk about that in the future. Okay. I didn't say from. Okay, it's from. Okay, so now for every person, we're kind of comparing the person's mark with the average mark in that course. So Alice took 2521. She got 85, which is great. And then whereas the average is only 72.5. And then Alice also took 3311, and she got 88. And we're comparing that with the class average, like in this way. So this is important. And let's make use of this view. So now we want, for students enrolled in a specific course, we want to find the people whose marks are lower than the class average. Well, I usually don't do that, but I think I heard some professors do that because they like to look at a distribution of marks and then decide, okay, half of them, maybe 1/3 of them fail, and then I don't like to do that. I like to believe that if you got enough points, enough marks, then it demonstrates that you're good enough to pass. You're good enough to be HD. But some people, I think, especially I think from the U.S., the American universities, and can anybody tell me in the American university they have a concept of curve. So you got they make a distribution curve for students, and then they cut the end 10% and fail them. I feel like that's just cruel. But there's one way to do it if we know how to use if we know how to compare to the average mark like this. So basically, we can make use of the view that we have just created, and then put an additional constraint. We're filtering the people with the mark less than half of the average. Let me see. So specifically for 2521, okay, nobody. Great. What about average? Well, 2 people were below average. Anybody exactly at average? Nobody. Anybody larger than average? Okay, 2 people. Okay, that's a pretty nice distribution. 2 people on the right-hand side, 2 people on the left-hand side. Okay. And now let's look at joins. So we already talked about why we need joins, because we need to extract information from different tables. But it turns out that joins have different variants. And there are, I'm going to go back to this. I'm going to talk about a type of join first. There are natural join, there are inner join, and there is left outer join. And for inner join, you need to specify, let me find an example of inner join. For inner join, you need to specify the columns on which you're joining. And for natural join, a natural join is a very messy way of writing joins, in my opinion, because what a natural join is doing is that it's looking at 2 tables and then is going to automatically assume that you're going to join on the tables with the same names. And so natural join is a special case of inner join. So I don't recommend you do that unless it's the easy schema like we're looking at these days. So I always recommend not do natural join because it creates more problems than it solves. I believe whenever you write a join, it should either be an inner join or a left or outer join. For an inner join, you're specifying the columns on which you're going to join. And then for outer join, the only difference of an inner join and outer join is that for a left outer join, what you're doing is that you're keeping all of the rows for R, and then you're trying to match the tuples for R and S, and then you need to grab the tuples from S and then put that next to R where it is matched. And this will create a problem because not all tuples will be matched to R. It will create a bunch of holes in the result table, but sometimes that's what people want. let's look at some concrete examples. So consider these two tables. So these are abstract tables. We got R and S, and here we only got 3 columns. So we got 2 columns for R and 2 columns for S, and these are the data. And let's kind of look at the result of the set operators as well as joins. See that? I hope these tables are already created. Okay, tables are created. Let's look at how we. Okay, so for union, so let's look at the R table and the S table. So R table has A and B, and S table has A and C. And if you're doing the union, it basically stack them together. And if you want, and for intersection, you're finding the tuples that occur in both tables. And for exception, you need to find the tuples that are in R, but are not in S. So we can kind of use an I test for R intersect S. So this row is the intersection because that's the only row occurring in both tables. And for R except S, you need to look at all of the tuples in the R table, and then you need to check whether it is in S. If it's in S, we need to remove it, and the end result will be the difference. So let's look at the intersection is B2, and let's look at it except 3 tuples from the left-hand side, and obviously this one is removed. And let's now look at joins and natural joins. So when you're writing joins, what you're doing is that you're really specifying on which columns you're joining them on. So that's make it larger. So for a normal join, which is the way it's supposed to be, you need to specify that in the R table, we're matching the A column with the A column in S. So in that case, we ended up with this. But in natural join, it is a lot more messier because it assumes they have some common attributes and they will just join on common attributes. And they will only return the common attribute once in the end result. So in this case, R has A and B, S has A and C, so they'll automatically join on the A column. For simple databases like we're looking at now, this is fine, but for more complex databases, you'll see when you're doing the assignment, a lot of times if you just do a natural join between these tables, it's very confusing on which columns you're joining them on. And lastly, the left outer join. So the left outer join, you also need to specify on which column you're joining them. So let's look at the size of them. So look from R, we got 4, and from S, we got 4 of them as well. And what it's doing is that this is a left outer join from R to S. So R is on the left-hand side. So basically, R is the relation on the left. So in the result, what we'll expect is that we'll expect the original R table to be present in the end result. What we're doing is that they're matching on A, and we're looking at each row in the S table. God, it's way too big. And we're trying to match that to the A values in R. And then if it's matched, we put that in here. And if it's not matched, for instance, in here, the A value is C, but in the S table, there is no A value with C. So in the end, we'll expect a hole in here. So we usually use left outer join when the left table is significantly more important than the other table, that we always want to look at those columns no matter what, even if it creates empty holes in the database. Okay, let's look at the end result. Okay, as you can see, these three rows, because they're matched, so they have values from the S side. And for C, nothing is matching C. So nothing is matching this row, because it requires the A value to be C, and in the second table, the A values are A, B, D, E, so no match. So there's a hole in here. Yes?
Can you do like a with and right outer join so that the E row would also stay?
Pardon?
Can you also keep the E row and do like a with and right outer join at the same time? So
Keep what? Keep which row? You mean the E row? I think you could do that, but we usually don't do that. But if you do that, we will have 5 rows in the end. So basically, we're doing a left outer join on this table, and then we do a right outer join on the other table. But you need to specify. So this is the end result of the first join, right? So what if you want to join that back to the right table? Then you need to specify on which column you want to join that on. So there's no choice. You can only join on A, because A is the only common attribute in here. And you end up with more columns, but you will have one more row, but that will create like more holes in the database. Okay. Okay, we have demonstrated union except. Great. And so we usually do this when R is significantly more important than S. For instance, R is like a student table, and S is like, whether you have attended the lecture or something. Yes?
For natural join, if there are more than one common columns, will it just randomly pick or just the first?
They'll take all of them. So if R has, so in this case, they only have one common attribute. But in real tables, as you can expect, they may have 10 common attributes, and they will try to join on all of them. But and they will not look at the schema. They will not really look at the schema and see whether those attributes with the common names are actually the same foreign key pointing to the same thing, because we could have a student name, and you could have a course name, and they're all called name, right? But if you do a natural join, they'll just say, let's match name with name, and it will be a disaster, because you cannot match a course name with a student name. So a natural join only works when you have very simple database, and when we have like student enrollment, things like that, you always want to specify this is a student name, this is a course name, and maybe this is a beer's name. Okay, that's a good question. Okay, with, let's talk about with and take a break. So with is kind of like an auxiliary query, but you'll be wondering, like, we already talked about helper views in previous lectures. Why do we bother with auxiliary queries? So the reason why we need that is because you can get away with not using it ever, but it may make some of your queries cleaner. So what if you want to create a helper query that is only useful for the specific view? Let's just say that you're creating a very specific view, like the beers liked by John. And that piece of information may not be useful elsewhere. It's only going to be useful in our first query. So what they do is that they don't create a separate view for it, they will just put that in the width, and they kind of declare the view in line, which can be used in the main query. So they define it like this, and then they can then use the previously defined query. So we can define it like here, and then you can use that here. So for our previous subquery example where we want to find the beers, the bars sell beers that John likes, then we can, the way we did that was we used the subquery, but what we can also do is we can wrap one of the queries, we can wrap the first helper query into the with clause, and then we can define it like John likes, and then we can just use that. We can just use John likes as if it's a view defined elsewhere. But nobody else can use this view when you're outside of this query. So when you're using with, it does not create a view in the database. It only creates kind of like a temporary view within the same query. Okay, let's take a break for 10 minutes, and then we'll come back with more SQL syntax and PLPG functions. Pardon?
I was wondering when the assignment will be.
Oh, it will be released tomorrow. Yeah. Right. So with is basically a temporary way of writing an auxiliary query. And there are a couple of more syntax you should probably know about, but you probably don't use them a lot when you're solving problems. So these are just basically telling you these are the possibilities as well. But so you can also write the local queries in the from clause, and it will also be treated as like a table. And also you can write the with clause recursively. And now let's talk about why we need something beyond SQL. So as we have mentioned, SQL is more like a declarative language and is great for querying, and is great for data definition, is great for data manipulation. The thing with SQL is that we don't really have a way of ensuring that our operations are transactional. So transactional databases are especially important for your brokerage account, your bank databases, and where security is very important. So we actually mentioned this example in the first lecture. So this is the transfer money in the bank account example. So if in the bank account, in the bank scenario, when a customer attempts to withdraw more money than they have, they indicate insufficient fund, and otherwise we need to update the account. So let's look at how we should do this with SQL alone. So, and ideally we want the whole operation to behave in a single or nothing action. So we don't want, the person to be able to withdraw money, but their account balance is the same. And also, we don't want them to withdraw money when they have insufficient funds. So this is how we would do it purely in SQL. First, we check whether they have insufficient fund. So that basically we're using a SQL query to check whether you have enough money. And then we make the update no matter what. So we make an update to the account, and in the end, we display the new balance. And the first thing is checking whether you have enough money. The second statement is actually updating your balance, and in the end, it prints the new balance in your account. It looks, on paper, it looks okay, but there are a couple of issues with this SQL-based approach. So first thing is that all of the numbers are basically written in here, and it is very prone to attacks, and it's not very secure. So if you work as a backend engineer, you should know the concept of SQL injection. So if they allow you to input pretty much anything into a field that will basically later be put into a part of SQL code, what they could do is that they could do they can do a semicolon, and then they could then select and print the whole database, and then they can steal your whole database. And another thing that's wrong with this approach is that there's no guarantee that these three steps will work in a or nothing manner. So maybe in the first, maybe we discover they have inefficient funds, and then it does the update anyways, and then it will print the new balance. And also, we need to evaluate, we need to compare the balance and amount twice in this implementation, and it doesn't really allow parameterization. So whenever we have, let's say we have a new account and we have a new amount we need to withdrawal, then we need to write this thing completely different manner again. So what we want is actually from this is what we want in a real system. We want maintainability. We want we want it to be atomic, so basically all or nothing. And also, we want to be able to ensure consistent behavior under concurrency. So what it means is that what if after you do this first select, somebody else is changing your database, and then you make the update, and then somebody else changes your database, and then your values are wrong again. So we need to make sure that the system is maintainable and it goes through in an atomic manner, and also we can kind of maintain the concurrency. So this is kind of like related to the second half of our course, where we will talk about transactions. So what do we need from database programming? So right now we have talked about we can do data manipulation, data definition, but we need more control over the data. And we need to borrow the procedural programming component of C++ and Python into SQL so that we can do more things. And this is the actual solution in PLPG SQL function for the withdrawal problem. The reason why this is a better solution, first of all, it has a control flow. So it computes how much money you have and then store that into a variable. And then it uses an if statement to compare the amount you want to draw and withdraw, as well as the money you have in the bank account. And it only proceeds the update statement when you have enough money. And also, it declares that the amount should be an integer and the account number is a text. And obviously, when you have an input parameters like that, you can do all sorts of input control, and you can kind of check whether this is a legitimate account number or whether this is a legitimate amount. And most importantly, everything is wrapped up into one giant function. And when you're actually using this function in PostgreSQL, you do something like select star from withdraw, and then account name, and then the amount. What it does is that it automatically treats your whole SQL statement as one transaction. So what if it fails here? So what if it prints your balance first, and then end of the world, Iran attack or something, geopolitical conflict or some other countries attack your data center, and then the whole system crashes here. And then what should we do? If we wrap it up in a transaction, the least we could get from the database is that when we recover the database, we should be able to recover it to a consistent state, which is all or nothing, which is either at this point where nothing has happened, or at this point, everything in this function body has happened. So that's why we want to use procedural programming language in SQL, and that leads to PostgreSQL store procedures. So there are two types of functions. So basically, we're talking about functions. There are two types of functions you'll encounter in this course. There are SQL functions, which are simpler, and there are PLPG SQL functions. And for SQL functions, you are returning a table. And for PLPG functions, the return type can be much more, you can pretty much define any kind of return type. You can return a text, you can return an integer, and you pretty much get to return, you can pretty much define what you want to return. And in both cases, this is the syntax. You want to create or replace a function, and you want to specify the arguments, as well as the return type. And between these double dollar signs, this is the function body. This is where you define the variables as well as the control flow, the where statement, the if statements. And after the language, you need to specify whether it is SQL or PLPG SQL. So the only two languages here are SQL or PLPG SQL, where I think they may support more languages, but in our course, we're only going to stick to PLPG SQL as well as SQL functions. And so this is a typical structure where we have a function name, and within the function body, this is we can declare the variables that we can later use, and then the actual procedural part is stored between the beginning and end. So in here we can do both SQL as well as control flow. So control flow is basically like a while loop or a for loop or if statement, things like that. And we can store them into variables and then compare those variables to the table. So we can do all sorts of crazy stuff. And I want to make a remark about the PLPG functions. So before we had a better interface between the back end and the application layer, this is pretty much everything that we rely on. We have to rely on this. But after that, we have a huge leap. So we are able to deliver a lot of that application a lot of that computation in the application layer. As you will see in a couple of weeks, in this course, what we're doing is that you could use Python to connect to your database, and then it establishes a connection. It does some basic extraction of data from the database, and then you can do data cleaning as well as more complex data analytics using Python. So basically, we're giving you two choices. You can either do the complex computation in PostgreSQL, where you probably use a lot of the procedural language in here, or you can send that data to Python and then ask Python to handle that. And Python has pandas, they have NumPy, they have things like that. So we're offering some options here. And so this is the complete picture of the withdraw function that we talked about. And the withdraw function is a PLPG SQL function because it involves the control flow. And so when this is a SQL, you can only write SQL statements in here. When it is a PLPG SQL, you can write if statements and while statements and things of that nature. So in here, we can first declare the balance. So we can declare the variable balance, and then we're performing. So here, we're also allowed to perform SQL operations. We are writing a SQL query related to the input parameter. So this is pretty new to us. Before this, we were only allowed to write views. So basically, they are kind of fixed view of the database. But now we can make you can consider functions like a parameterized view. So now you can consider this as a view, but instead of matching to a specific account number, you match that to the input account number. So basically, this can change. The account number can change, and you're doing the query based on the account number. And after that, you can do some control flow. You can compare whether it is whether you have enough money or not. And if you do have enough money, you can go ahead and do the update in the database. So you're deducting that amount from the balance, and then you can return the new balance. You can return a new balance. So what is the return type here? The return type here is a text. So here it is returning the return text will just be new balance column and then an integer. So that's and you can make other return types as well. And you can return a set of tuples, or you can return a table. You can return an integer, and you can return text. Yes?
Why do we have underscores?
Underscores?
Like for count
That's just a naming convention for PLPG SQL functions, because honestly speaking, PLPG SQL functions, the syntax is kind of old. So what they usually do is that when they're defining variable names, they use underscores. And okay, I think we have looked at the withdraw function, and let's look at a couple of more examples. So maybe we should demonstrate this as well. So imagine we have a library borrowing system, and we have a bunch of tables called members, and also we're storing the books that they have already borrowed. And what we want to do is that we want to create a function to handle the borrowing action of a member. So if you want to borrow a new book, we got to check a few things before you do that. So that's kind of standard in transactional databases, because we cannot just allow you to do things, to do whatever you want. And if you think about it, when we were using data definition language to create table commands, to write constraints, there were certain constraints that we were not able to implement, like the subclasses, like the overlapping subclasses and triggers and things like that. And those things, they can 100% be implemented using SQL functions as well as PLPG functions, because now we have like control flow, which is powerful. So basically the logic is we need to check whether they have reached their borrowing limit. So obviously you can only borrow a certain number of books, and if the limit is reached, we say cannot do that. If not, we insert a new record into the borrowing table. So let's look at some data. So what are the tables that have already been created? Okay, I think borrowed. Okay, so this is a borrowed table. We're storing the member's ID, we're storing the book's ID, and we're storing the borrowed date. And here it says that, so it's always very useful to read the description of the table so that you understand whether your database has only one table or you got a bunch of tables that are linking together. So here it says that the member ID is actually referencing members ID. So basically this tells me that there is another table called members. So members, and I think that's the only two tables we got. So members and borrowed. And this is the function that, let me investigate what are in here. So we got 3 members, Alice, Bob, and Charlie. And borrowed, we got about 6 records of people borrowing books. So basically, Alice, Bob, and Charlie borrowed a bunch of books in the library, and this is the record. And I think we need to define the borrowing limit somewhere. So let me just run this PLPG SQL function, and okay, not this one. This is withdraw. Okay, this is borrow book. This is a PLPG function. Okay, let me just. Thank God I found this interface, because I cannot handle this in the CSE VLab gateway. That's a disaster. So if you look at the table, I think it should list. How do we use this function? Okay, so select star from this function. Let's just use this function and see whether we can borrow a new book. So members, we got these people, and what about books? Borrowed. Okay, we got these books. Okay, so let's try to borrow a new book for a member and see if that goes through. So we can do borrow book, and then the member ID. Let's ask Charlie to write another. That's so basically everybody has the limit, the maximum number of books that they can borrow. Let's ask Bob to borrow another book because he only borrowed 2 books. So Bob has an ID of M002, and then the book that him borrow B101. I'm not sure if that's okay. Book borrowed successfully. Well, let's see why. So basically, before this, Bob borrowed like only 1 book. That's Bob, M002, but he can actually borrow 2 books. So we borrow 1 more book. It went through. Let's see if we can borrow another book. Okay, it says borrowing limit reached, because now borrower is trying to borrow the 3rd book, and this is not allowed. So do you think there's something wrong with this database that you find weird? Because I think there's something very weird about this database that I don't like. What is the important entity that is not modeled here? I think we should have at least another table called books. And then it lists all of the book IDs. And then it lists number of books available in the library. Because right now, what it's doing is it is assuming that every book has infinite number of copies, and you can borrow the same book like 1,000,000 times to 1,000,000 people, and it doesn't really check that. So basically here, what it does is that first it counts number of books they already borrowed, and look at the borrowed table. So this is the part where it's very useful. You can actually store the information from a SQL query into a variable. And a lot of times we store an integer or we store a text. And here we're storing an integer because we want to get the number of books they have already borrowed. And so we declare this as an integer, and we declare it as an integer, and then we can select the count into this integer. So basically, this is storing the number into the integer. And then we can compare that with the maximum number of books that a specific person can borrow or not. I think it's kind of messed up that they have different limits for different people. I thought they should have like a universal limit or something, but whatever. So basically, you can also put SQL queries within the conditionals. So the borrowed account is a borrowed number. So this number is something that we just computed. We selected that into this number, and then now we're comparing this number to the result of this query. So we're running a small query here to compute how many books they can, so 5, 2, or 3, how many books they could borrow. Another way we can do this, maybe make it less messy, is that we can make another SQL statement here. We can say select max books into limit from members where member ID is equal to the input member ID. And then we can just compare 2 integers in a conditional. That looks a bit nicer. And if that's exceeded, we return borrowing limit reached. And otherwise, we insert into the database, and then we insert a success message. And another thing I don't like about this example is that when the user is trying to do something that we don't like, we don't just return a message. We should raise an arrow or something so that this event is escalated to the database. Because right now, it only kind of prints a message saying that, okay, you cannot borrow anything anymore. But usually what is done is that they raise a notice or they raise an arrow. Okay, let's look at some SQL functions. So this is a much easier one. So a SQL function, to specify the language of the function, you need to write it here after SQL. And everything between the double dollar signs is the function body. So here we're defining a function where we want to find the pricest beer, the maximum price at a bar. What is the most expensive? We want to find the most expensive beer, the price in a given bar. So before we learn PLPG functions as well as SQL functions, we could only do views. So basically, we could create a view called the maximum price at region hotel, the maximum price at Australian hotel. And for that, in that case, we'll need to create a bunch of views. And the input is not really parameterized. And here, what is nice is that we're actually able to parameterize the input, which is the hotel name, which is the bar name. And note that here we didn't have a variable name in the input, and we just specified a variable type. And this is okay as well. And we have the inbuilt $1 to represent the first argument taken from the function. So basically, you can put a text here, and then it will try to use this text to map to a bar, and then it will execute a select statement to find the maximum, the most expensive beers sold in that bar. Okay, I think we could probably copy that and okay, create a function. Let's use this function. I think another way we can use this function is that, so I like to treat it as a table, so select from maxed price at Australian hotel something. Let me try. Is that a legitimate bar? I'm not sure. I mean, I need to see what bars are there. Select from bars, limit 5. Australia hotel. Okay, not Australian hotel. Australia hotel. Australia hotel is a bar. And then this is how we can get the most expensive beer's price in that bar, which is $3.50. I think this database was created like a long time ago, where the beers are so cheap. We need to update that. So this is one way to use the function, but I think there's another way. We can basically select the function, and so there's a slight difference. So if you don't put, so if you put select star from that, it looks like a table. If you just select that, it's treated like a tuple. So looks about the same, so it's not a huge issue. Let me try another. I think let me try another one. What other? Region hotel. Okay, I think I've been to that one. Region hotel 220. Great. So okay, let's look at another example of SQL functions. So remember when we used when we wrote the withdraw function, we we kind of needed the PLPG SQL function because we needed to check whether the balance, whether we have enough fund, whether we can do this and that. But now, if we're just getting the balance of an account based on an account number, then a SQL function is good enough because we're basically getting information and we're not trying to modify the database. So let me demonstrate this function, get the balance. I think we can get the balance from accounts. Okay, I need to check whether we have accounts table first. So accounts table, accounts, okay. Let me check the structure of the database. We have accounts and we have account withdrawal and I think we have already created this table, so we don't have to create the table again. So let's see what is in accounts. We got 3 people with some balance, and now let's define this function. So basically what this function doing is that based on the input account number, you need to grab all information about this account. So, so this is one way to do it, and another way is let's do it too. I think we can get away with not using variable name. We can do $1 or something. So let's use this function and see what it does. Get account, and the account, let's try Alice 101, and it returns everything about Alice. And what if I define another function that does the same thing but with a slightly different input structure? So if I do get account 2, it does the same thing. So basically, you can you don't have to specify the variable name. If you're lazy, if there's not much computation to do, you can basically only specify the variable type, and then you can just do $1 and $2 or something. You can do $2, $n. Okay, let me look at more examples. So max price add, we have already done that. And prices to beer, we have already done that. And now let's look at another example. We need to find the most expensive beer that a person likes. So so this is one way of doing that, and this is not a very good way. I think we mentioned the reason in the last lecture, because what if there are multiple beers that maps to the maximum price, and in that case you only get in the one of the beers. So I'm going to demonstrate another way of doing this. So first we're going to create a helper view, and then we're going to use the function. We're going to ask the function to use the helper view. Let's first examine the behavior of this function first. So let's define this function. Let's define this function. Okay. Prices. Let me find this. I think I find. Okay. I think I have this function right here. Okay. Here. Can we copy that? Okay. Okay, everything between the function body. And let's look at this function first. So we need to find the the priciest beer a person likes. So that's first to write, let's kind of look at this SQL query first, and then we'll look at whether we can phrase that into a function. And obviously the input parameter is the drinker's name. So the input parameter is drinker's name. Let's just say that we want to find out for John. And maybe here we need to say this is else beer. Okay, I think that's the reason why it didn't go through. So for John, we need to first look at what beers he likes, and then we need to map that information to the sales table, and then we need to grab the one with the highest price. And the reason why it didn't go through is because multiple tables have the, so for likes table, it has the column called beer, and then for the sales table, it also have the column called beer, and it's confused which beer you're talking about. And let's run that function again. So this should work, and let's use this function to find out the prices beer for John. For John, it should be the same thing that we've just looked at. Prices, select from, okay, from here is 3 sheets. Have anybody heard about that beer? I've never heard of it. Okay, how do you make it right? So this is one way of doing that. So another way is that we can use, we can create a helper view. We can create a helper view. So create a helper view, and then we can use the helper view in the function. So let's create another function that is slightly more robust. So let's call it pricist 2. And first, let's create a helper view, which is let's create or replace view called I'm just going to call it helper, and then we're gonna take that information, and we're going to create a view for it. So let's just get this whole information and select everything. So the way we're doing it is that we want to find the correspondence between the person as well as the beers they like, as well as their price. And then we can use a helper view to compute the maximum price corresponds to the beers liked by this person, and then we can map that to, and then we can map it back to get the beers. So first of all, let's get the drinker, and then let's get the drinker, and then let's get the beer. So s.beer, and as well as price, s.price. Okay, let me look at that. So I'm doing this step by step. So this is the info. This is the helper view that is useful for us. Wait, why don't I see John here? Okay, John is here. John only likes 1 beer, and Justin likes 4 beers, and Adam likes a lot of beers. So Adam likes the new beer and then sold in different prices. Okay, and so this information is very useful for us because with this helper view, we can, for one person, we can compute the maximum price, and then we can map that back. So this will be our first helper view, and then in the function, we can basically. So this is how we can. This is why views are super important. We can not only use views in other views, we can also use views in functions as well. So in here, what we can do is that we can first compute the maximum price. So basically, we can do we can organize the maximum price. So maybe I should do a maximum price here. So I should just do the drinkers and the price, and I should create another view called the maximum price. Okay, just going to call it max price per drink, max price per drinker. And in this case, we're just going to group by the drinker and get the maximum price. Okay, put the max in here, and then it should get for each drinker what is the maximum, what is the most expensive, what is the price of the most expensive beers they got. Okay, this is that, and then so we got one helper function, two helper functions, and in the final function, what we can do is that we want to select from the first helper function, where the drinker is matching drinker, where going to call it H, where H dot drinker is matching drinker, is underscore drinker, or we can just do $1. And then we also need to match that the price is basically the maximum price corresponds to this person. We want to select the maximum price, max from here, where the drinker is, where m.drinker is matching this. Okay. Let me first define these helper functions. Okay, let me check if it's something that I have in mind. Okay, that's define another helper function. Okay, and then let's define this function. Okay, I think I need to. We need to grab the actual beer names. So let's first return. We need to return the helper functions. The helper functions beer name. So basically, we need that as most expensive. Okay, not create new names for it. Okay, this should work, and then let's define that, and let's use that for John. So select from our new function. I hope this works. Let's look at for John, it's 3 sheets, and what about for another person? Let me see the helper function. Let's try Adam. So for Adam, Adam always drinks new beer, and so whatever you put in here, it will be new beer. Let's try Justin. Justin likes a bunch of beers, Victoria Bitter and sparkling. So the sparkling one will be the more expensive one. So if we put Justin here, it should get the sparkling one. Okay, Justin. Didn't spell it right. Justin, yeah, sparkling one. Okay, so basically, if you're doing it like this, this example demonstrates that we can use views we can use views inside of a function, and we can break a very complex question into smaller steps using helper views. And this should be very useful, especially in your assignment. Let's move on to let's move on to the other examples. So this is a factorial example. Basically, we can use PLPG functions to compute the factorial of a number. So I don't think this is very useful because it does not really manipulate the database. It's only here to tell you this is what we can do using for loops. So basically, there are two ways to implement the factorial function. You can do it in recursion, or you can use the while loop to do it iteratively. So if you have solved LeetCode medium questions, this should be pretty straightforward to you. And the last thing we want to emphasize is that for PLPG functions, we can not only return text and integers, we can also return a set of tuples. And when we are returning a set of tuples, or we are returning kind of like a table, we need to use the return next statement. So let me give you an example. Here, we need to return a set of integers. So in the end, we're expecting a column of integers. And how do we prepare that result set? So for every row we need to pad onto the result set, we need to put it after return next. So basically, for every i is kind of incrementing I, and then for every I, it passes on the underlying result set, and then it builds on the result set towards the end. In the end, it will automatically return that set of values. So if you look at this function body, what's weird is that you don't really see a return in the end. You only see return in the middle, and it's actually return a set of integers. So basically, every time we hit a new value here, we are padding it onto the result set, and then upon termination of the function body, it will just return that result set to you. So this could be kind of confusing for beginners because it's not quite like our usual procedural language where we kind of explicitly say, hey, return this hash table, return this list. So here is saying that we're returning the elements one by one, and in the end, you should see a list of values. So this could be confusing. And another syntax that you need to be familiar with if you're working with PLPG functions is you can actually combine a SQL query with a for loop. So this will be super important because this is kind of the reason why we introduced PLPG functions in the first place. So we have a huge table, and in SQL, the best we can do is that we can join them, we can map them, we can manipulate these columns, but we cannot really do things row by row. So if you want to do things row by row and apply a different logic to each row, then this is what you can do. You can wrap that into a for loop. So basically, this will go through every row in the result of that query. The result of that query will be a table. It will go through every row of that table, and then it will return that row. So this is kind of equivalent to the effect of a SQL function, but what we could do is that we could actually compare. So for beer record is actually a row type. So imagine we have a table, and beer record is representing one row in that result set. And we can do things like beer record percentage sign beer type or beer price, things like that. We can use it in an object-oriented manner. Okay, so that's a good place to stop, and we're working on the practice 3 video, and we think it should help you with your assignment. and you should expect it in today or tomorrow. And tomorrow we'll actually release the assignment. So next week we'll talk more about PLPG functions, SQL functions, and after that we'll talk about how to use Python to connect to the database. Okay, that's it for today's lecture. Everybody have a good weekend. I'll stick around if you have questions. Thank you. Wait, I think it's not on the website. It's in the wait. I think I mentioned somewhere is in. You know what? I'll make an announcement about it. It's in the. It's on the server. It's on the server. You got like a copy command and then. So you got to copy and then dot. Copy the SQL files. Yeah, I'll make an announcement about it.
Sorry, just quickly.
Yeah.
You know with the dollar signs, where you have like dollar sign when you don't have a variable name, but you can put like a
$1, something like
$1.
yeah.
Is there $0?
No,
Okay.
just $1 starts from 1.
Yeah, because in like bash scripting and stuff, it starts from 0 with like all of the file names, and then it goes to arguments. So I was just curious if there was $0 in this, but
Yeah, it's
just $1.
Yeah, just $1.
Okay, too easy.
Yeah,
Cheers,
it's
thanks.
good question. Yeah.
Thank you.
Thank you.
Hello. Yeah, sure. You want to put it here?
Yeah, sure. Did you write something about, like, is this? So in this, you read it as, like from A to B
Mm-hmm.
is many to many. And
One to many.
why
one
is
to
it one
many.
to, from A to B?
From A to B is one to many. Because A has the arrow pointing towards it, so it is the one side. So this is the many side. This is the one side.
Oh, okay. I
And
was getting confused.
so this is kind of like, let me see. This is one lecture, and this is one course, and this is with students.
Yeah.
So students take one course, and course can be taken by many students.
So it's like, so when you read it, like A to B is actually like B to A, because it's like, so many B's to one A, because the arrow.
Yeah, many B's to one A.
Yeah, and then, so one A to many B's. So it's,
Yeah.
Okay. Yeah, that was it. And could you, I don't know if you're allowed to help with this, but I set it up, so like I set it up so it would fully work,
Without a source.
without a,
Okay.
but then
Okay.
now it's like not working. But now it's like, it's not working. Like, I don't know what happened. Like, I set it up.
Wait, you cannot even. So now you
Get
cannot
in.
even get into the
Yeah,
CLC
I
server.
can't. Like, because I set it up so that all I type in is my passcode and I get straight into the server. But now I tried it today and I can't even like get into anything. Well, this one's because I was looking at the answers. But if I just go into like SSH,
VXDB02, right? That's correct.
and then it'll like, but it's taking so long to load and I can't even enter my passcode. It's like not letting me in anymore. But I don't know because I was using terminal.
That's very weird. What does it say? Okay, post it on the forum, and we'll have
Okay.
somebody look into it.
Okay, thank you.
Yeah, I have no question, but I can't access the quiz right now.
Which quiz?
This one. Not the submit marker, just the original one.
You cannot do that because it's passed.
Yeah, but that's a quick question about it.
Oh, okay. Wait, why I cannot?
Yeah, I can do this.
everything's free?
Yeah. Well, I said at the end of the, so it will be like, I think they're working on it today, tomorrow, something like that.
Yeah, get it. And then we will release the assignment one at today, tomorrow.
Simon one tomorrow.
Thank you.
Okay, looks like I cannot open it either. That's very weird. When it's passed to, okay, let me look at the previous offering because they should have the same quiz. Yeah, I'll have to look at past 10. Wait, cannot get web CMS? What?
Yeah, I can't get into my sim.
Cannot. Okay, then there is. Okay, now I think there is an issue. I think the server is down. I think that's why. That's why she couldn't get into the server, and then we cannot see. Let me see if the server is down.
Yeah, I just yeah.
Like if you cannot get into Web CMS, then that's yeah.
That's fine. I used to be fine to get into CMS, but
Yeah, usually because they got a server outage or something. Can when it works, can you post it on the forum?